Welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're joined by Dr. Farid Salama from NASA Ames Research Centre. Farid got his PhD from the University of Paris in France. He was working on vacuum spectroscopy and high-energy UV spectroscopy of molecules. He then came across to work as a postdoc at Lawrence Livermore Lab in Berkeley. And then did a postdoc at NASA Ames, NRC postdoc, and then has remained at Ames ever since, working in the astrochemistry lab. Today he's going to talk to us about polycyclic aromatic hydrocarbons and their spectroscopy and their importance in the interstellar medium. So if you'll join me in welcoming Farid.
Thank you for the introduction. Thank you also for the invitation to speak here. It's nice to be back to SETI. I've often been around. What I was asked to talk about is basically the low temperature spectroscopy work we do and what we learn from that, what we gain from that, and how do we apply that to support astronomical observation and of course support NASA space missions. This is supported by NASA. So, as it was mentioned in the introduction, I work in the astrochemistry lab, which is now officially the astrophysics and astrochemistry lab at Ames. The web address is indicated below. And the way I would like to go through this discussion is a short introduction about the context. Why do we study pH in particular, or carbon molecule in general? And the DIBs, this pending problem, this important mysteries, long-standing problem in astrophysics, and the core of our work, which is how do we approach this issue from the laboratory point of view, and more than that, why these astrophysically related issues are so important also to basic science. So it's a two-way between molecular physics, chemistry, and astronomy. And the observation, what do we get from the lab? How do we interact with the observation? And what we've learned so far, and what, of course, will be taking us. So to get in the context, you are all familiar with why carbon is important and the life cycle of carbon in the galaxy. So basically, carbon is an important element because it has a very rich chemistry and it appears in different phases, going from the ejection when in stellar dust, feeding diffuse interstellar medium with very low density, high energy environment, and then cycling through denser clouds where small grains are formed, they get coated by ice, and then ending up eventually in accretion and the formation of planetary system. The region I'm going to focus on today is the diffuse ISM, for the reason that we work in the UV visible, which is an energy range where this medium being diffuse enough, you can still see light through absorption. In dense medium, usually saturate, you won't see your UV light, stellar light, but you will see emission in the infrared, which is, by the way, the basis for the PA model. So today, I'm going to talk about the diffuse ISM. By the way, we also study planetary atmosphere in the lab. I'm not going to talk about this today because there is no time, but the same logic and the same facility, because it's a complex lab facility, can also be applied to problems like the atmosphere of Titan. I'll say very few words if I have time at the end. So just as a reminder, I'm sure I don't need to remind you of that. I just wanted to highlight the difference because many people, Ames being strongly oriented infrared place, a lot of work happen in dense, targeting dense molecular clouds. Here we're talking about diffuse cloud. As you can see, the difference in densities are order of magnitude in terms of the interaction, and the temperature also slightly warmer. So basically, when we work in a lab, we will tend to be less than 100 K to simulate the temperature. And of course, you notice also the difference between the flux of photons and so the energy being to which those species are exposed. So just remember again, we are focusing on carbon, and those are the ingredients of interstellar medium in our galaxy and in many galaxies, and it makes the interaction quite complex. So the basis, everyone is familiar with the infrared emission band. Those are emission features that are seen in the infrared. They're very well known. They're seen in a wide variety of environment in space, from the diffuse ISM, reflection nebula, star-forming region, planetary nebula. They are seen in our galaxy, in external galaxies, so they are considered as a probe of something that it's widespread, very ubiquitous, and there have been a lot of work on this. Ames has been a pioneer in this work with people like Lou Alamondola and Xander Thielens, and their interaction with the PA model. So basically, models have been put forward to explain infrared emission. There have been a consensus that this emission is due to emission vibration from aromatic system, and in particular structure like polycyclic aromatic hydrocarbon, or PA, which are carbon-hydrogen elements. So they are fused benzenoid rings with hydrogen on the side, and the difference vibration being stretching in plane bending and out of plane, so forth, explain nicely the infrared emission bands. Of course, it's not explained by one or two of these molecules. It's much more complicated than that, because we're talking about space, we're talking about the distribution of carbon, and when we say PA, you should take it in the very broad sense, a very loose sense, in a sense aromatic system may be compact, non-compact, have chains or not. The bottom line is that here we're talking about infrared emission, so you have basically your molecule in a rest state, in a ground state, and it's been excited, pumped by UV photons, and it will emit in the infrared. Though now there is, I would say, a very strong consensus in the astronomical community about these infrared emission bands are often now called the PA bands. So that's making for PA being very widespread in space, in our galaxy, and in other galaxies. But we need to understand also how those emissions are being pumped, and also what are the characteristics. That's just a very small cartoon that basically shows all the form and shapes. You have a structure component, you have a size component. So the idea, like in any science problem, first thing we try to do is get some information about basic property and see if we can constrain the problem and kind of catalog things according to their specific properties. So you can see different shapes, different size of PA. So to summarize, here a structure, for example, being compact or non-compact, you can see that you will have a stability issue. A compact system will tend to stay, to be more resistant to destruction, for example. And what I should mention, why those PA are so popular, is because they are very stable molecules, because they happen to have delocalized electron over the carbon skeleton. So they have what been defined as double bonds, which add strength to the skeleton of the molecule. And by the way, we are all familiar with those pH on Earth in pollution and atmosphere. Now PA being so involved with the infrared bands, and now been kind of an important topic on astronomy, they're being invoked in many topics. In some cases, there is evidence, in some, there is none. So let's go, for example, PA are detected in meteorites in a lab. I mean, so they are found in the meteorites and in IDPs. So basically, sample being brought back, they are detected. I mentioned the infrared emission bands. The PA are the best class to explain those infrared bands. Remember one point, we're talking about the infrared, we're talking about vibration. So vibration are characteristic of groups. They are not characteristic of specific molecule. So the infrared band are characteristic of the class of pH. They're invoked in emission in the visible in the red rectangle, a pumping mechanism of the SPA. They've been invoked in the diffuse interstellar bands. I will come back to that, which are absorption feature now seen in the diffuse ISM. And the logic being PA are stable. If they cause infrared bands, they are all over the place. On the other hand, you see diffuse bands that also are all over the place in the diffuse ISM. So common sense, you would think about a carrier that might be widespread, which doesn't mean it proves it. It's just a working hypothesis. There have been suggestions of some emission bands seen in the coma of some comets Halley, for example, due to some small pH, which, by the way, we will see later is not that surprising because polycyclic aromatic hydrocarbon have been formed in combustion-like process. So when you have a phenomenon with involving gas phase ejection with processing with high energy photons or particles, you may expect some aromatic being formed. And lately, the planetary community became quite interested in pH. I would mention the rings around Saturn. People are looking in terms of colors. Again, pH in the broad sense, like aromatic. And lately, Titan Cassini data returned very interesting data, very surprising to the community. No one expected that, which basically was a high mass detected, very high mass detected by CAPS and by the INMS at very high atmosphere in Saturn. And we know that Saturn has a lot of hydrocarbons and some orange-looking residue called toluene, which composition is not really well known. And there should be a link between small molecule and this solid and the formation of aerosol in the atmosphere. So PA are being seriously looked into this. So that's for the tour of the cosmic aspect. Let me get back to the wavelength range where I would like to talk about today. So this is an interstellar extinction curve, basically the extinction of starlight as plotted as 1 over the wavelengths as a function of the amount of material or the reddening of the star. And it's characteristic for most objects by a strong absorption, a strong feature in the UV around 2175 angstrom, which is called the UV bump. And there are also feature on the low energy side of the UV bump, which when we look more closely are those absorption feature tilted. So those are absorption bands observed in almost all line of sight in the diffuse ISM, and there are a big number of bands. I'm showing here the history of this problem to show you how important it became from first detected almost a century ago, and the number of detection increasing due to the improvement in technology, detector technology in the optical principally. But you can see now we were talking about until mid-70s about the problem of limited bands, and now we're talking about hundreds of bands according to the latest survey. And that's, of course, has a strong implication for the science, because here people were looking for one very widespread candidate carrier molecule. Now you're looking for one class or a few classes, chemical classes of compound that would cause absorption all over the place. So the diffuse band goes from the near UV now to the near infrared. There are, as I said, hundreds of them. It's the longest unsolved problem in spectroscopy for astrophysics. And it's important because, again, it's a probe of something that it's all over the place. Then knowing what it is will help understand the evolution of the ISM. And there's no discussion that the bands are interstellar. There are many ways to discriminate against stellar feature or of course, any telluric feature. And they're very stable because they are seen in very wide range of environment also. And they have different shapes and the profile that goes from very narrow band, 1 to 2 angstrom width, half maximum, to broad feature like 20 angstrom band. They are called diffuse because that goes back initially, people wanted to say that they don't look like atomic feature. And there have been debates over the years, what causes it. The strong point is that whenever you see diffuse bands, any diffuse band, you always see it at a constant wavelength, which is a very strong argument for a molecular gas phase origin as opposed to an impurity in a solid. Because you would, and also there is no preferred spacing between the bands, which is in spectroscopy, that's a very useful tool to characterize a molecule if you know the spacing between the bands. And there is a strong consensus about them being an indication of molecule in space. And the working hypothesis is that they're associated with electronic transition. Why electronic? Because we're talking about the near UV optical range. So this is the energy range where you would get electronic transition.
What exactly do you mean by constant wavelength? You mean not varying with time? Or?
No, you always find them. If you go look for the 5780, you find it at 5780. You don't find it at 5775 here and 57, like you would have with infrared emission band when you say the 6.2 or the 6.3. You allow some variation here. The bands are always found at a constant peak position. That's what they mean.
You said that meant it wouldn't be in the solid phase because
that alone would not prove it, but it works against, because if you take the hypothesis of solid phase, what would cause absorption like this would be impurity trapped in a solid. So you would I mean, statistically, you would need to have the exact, precise, same environment in your solids all over the place. It doesn't entirely disprove it, but it weakens it a lot.
In the gas phase, would there be similar constraints on the variation in pressure? Or?
No, that's what I'm hoping to show. If you can measure it in the right condition, and if you're talking about the gas phase, then you should not have that. And that's the strength of electronic spectroscopy as opposed to vibrational spectroscopy. That in theory, you get a fingerprint of a molecule that is really characteristic to its structure, because you get the electronic and vibronic bands. And so here how they appear as absorption. And as I mentioned, there is not much correlation between the bands. The only correlation that's been seen is with amount of reddening, basically the amount of material between the observer and the star. And these are some examples of diffuse band in our local galaxies. In HD 183143 is a characteristic DIB object that was studied, among others, by Herbig. And it's a very well-known object. And this EB minus V indicates the reddening or the amount of material. So they are seen in our galaxy. Extremely high resolution on some of the strong narrow band show substructure, and that was considered as a very strong argument for the gas phase, because it looks like a rotational structure like PQR bands. So that's added to the fact that you have the same wavelengths, you see this substructure when the DIBs are strong enough, because remember there are weak DIBs and strong DIBs. So to be able to do high resolution studies like this, you need to have bands like the 6614 angstrom. So the working hypothesis is molecule gas phase in our galaxy, in external galaxy, in the large Magellanic Clouds, the small Magellanic Clouds. Those are among the two most known DIBs. They are strong, they are well known, so they are often used as a probe to follow the DIBs in different environments. So you can see the Milky Way, our galaxy, and the same two bands being measured in external galaxy, also with some amount of reddening, and the spectrum on top that doesn't show the bands is usually for when you have less reddening. So it's used to cancel out the extra feature. And they are also seen in objects like M31 and M33, where they are actually quite strong. And why this is interesting, because again, those are external galaxies, but there are also galaxies where the ISM has very different physical environment, like the metallicity is very different, and you still see the bands. And remember, when I say the DIBs, now we're talking about the hundreds of bands, it doesn't mean that you necessarily see all the dip, but you see many of them. So that's how people, basically the DIBs is a box where we've been putting all the unidentified absorption feature going from the near UV to the near infrared. So to summarize, we have a perplexing issue, many bands. It's, in terms of spectroscopy, it's a fascinating problem, and lots of people have been working on that over the year, trying to solve this. So what do we do here at Ames in the laboratory to begin, before going to measure? I'm going to describe how do we try to approach this problem, because of course you're not going to simulate the diffuse ISM in a lab on Earth. But what do we need in our problem? What do we try to do? If we work under the assumption of free-flying molecules or ions, they should be free, cold, obviously less than 100 K, and exposed to some sort of energy, mostly vacuum UV photons. So the technique that was initially used, and which I'm going to show you some of the results as the basis for the next phase, because it will also illustrate how the field of basic science can evolve with astrophysical problems. It's a technique called matrix isolation spectroscopy. So at the time, you could not simulate in a lab free gas phase large carbon molecule, because there were no spectroscopy techniques sensitive enough to detect the absorption. So people would use solid phase, so basically use an inert gas like neon, argon, and condense it in a crystalline phase and trap, dilute inside it the molecule of your choice. So you trap it. Each molecule is totally isolated from the same molecule in different places of the solid. So you guarantee the isolation factor, which is essential, because remember, you want to look to one photon process for isolated cold system. And then you can probe it as low as 5 Kelvin in the case of neon and study your spectroscopy. But remember the downside here, trying to simulate gas phase, but you are in the solid phase, so you'll have to take this into account. But that's the kind of setup that do that. Basically, you deposit a film on a cold surface, condense it, shine your light, and detect transmission. And this, for example, shows some representation of pH like coronine, for example, being in a lattice. So by using this technique, it was very useful. We were able to do one thing that at the time was not known, is kind of catalog the spectral property of pH, and pH ion in particular. So this, for example, are all absorption spectra going from the UV, short about to near UV, from 2000 angstrom all the way to 1.1 micron. And by doing this, taking different shapes like here, pyrene with added rings, or and pyrene ionized, or phenanthrene, or benzogeisha, and so forth, some compact, some linear. We've measured many of these. What the idea was is trying to see if we can get some general features, general property that you can then turn to the astronomical problem and apply. How can we constrain the problem? So, for example, you can see here all the neutral one absorb in the near UV, the small one, but they don't absorb at higher wavelengths. As soon as you ionize them, you expose them to vacuum UV photon, then you get new transition, which happen to fall in the wavelengths domain of the DIBs. And that, in terms of quantum chemistry, is due to the fact that the pH have their all electron fillings, their orbital. When you ionize, you create a hole, and you generate new transition. So that's how you have transition in the visible. So we've been working, going from smaller size effect, trying to look to subclasses. Like here, you see it's like adding building blocks of your molecule and kind of getting a feeling what happens, what are the band characteristics of the neutral, of the positive ion, of the negative ion, and try to catalog that. I don't know why this is coming this way. It's probably the transition from one computer to the other. But it's okay. This is just to illustrate the fact that the message being that those pH, when they are neutral, if they are small, they absorb only on the UV. And when they tend to get bigger, you shift your transition to lower energy. You begin to go in the optical. But when you ionize them, they do absorb in the optical. So we tried to, as I said, to constrain that. And the way we did that is by looking size versus energy. So basically, this shows the size of your pH, the number of rings. If you multiply by roughly 2.5, it's a size, so that's basically 25 carbon atom pH. And the solid line shows the onset of absorption of neutral PA, because basically what you want to see, at what point do they begin to absorb, so should I consider them or not? So if you take the neutral one and the onset of absorption, and if you look between the two dotted line, which basically represent the widths in energy where you observe the known dibs, you can see that neutral PA will fall in the DIB range beginning at about 20 to 25 carbon atoms. So PA less than 25 carbon atoms won't be concerned. I mean, it won't have any impact on the DIB if they're neutral, which we've seen, for example, with naphthalene, which is 10 carbon atoms. But on the other hand, you have no upper limit, because basically your molecule grow, the transition are redshifted, and you get all sizes filling in your DIB. If you look to the ions, in this case, you look here again to the onset of absorption of your strongest transition, what you notice, you basically have no lower limit, because that's basically 2 carbon ring, which is naphthalene does already absorb in the optical in the range of the dibs. But you do have an upper limit of about 100 rings, which are about 250 carbon atoms. So it was a way how to constrain the problem, because you have a few hundred bands and you need to explain them by a few, by what type of position. And what I should mention is that years later, some people have run some evolved theoretical calculation to also look for a cutoff energy, and came for the ion to for the neutral to a value that is relatively close to what was measured before. So basically, you've kind of constrained your population. So we, at the time, that was about early, mid-90s, what was the situation? We had measurements in matrices. We had some known dibs at the point, and we could just compare the two and see how close they were, knowing that you cannot expect to get exactly on top of a band, because you're in the solid phase and you will expect some perturbation. So we did a survey at the time, some well-known DIB object. The idea was very simple: test the PA hypothesis against the DIB by defining a wavelength range. You can expect some sort of shift in position, so you would go to the astronomical band and see what falls in your box, basically, and have some pre-candidates. So that's what came out by comparing many of the electronic transition to many of those objects, some being weak or strong, and try to get a hand on that. So this is where we are. So basically, we've gained information about the basic, I would say, physics and chemistry of those PA, like, for example, what will happen when you pump them at a certain energy. Will you initiate infrared bands, or what type of absorption you have? But you don't have lab data that you can use against the observation. So came the next generation experiments. The idea, as I mentioned, was to try to do this in the gas phase, because you know that you need to adjust your cell. But to do it in the gas phase, we needed a higher sensitivity technique. And by the time, early mid-90s, a new technique was developed by people here, our neighbors in Mountain View, Tony O'Keefe and others, called cavity ring down spectroscopy, that increased by orders of magnitude the sensitivity you could expect from transmission measurement. So now it was conceivable to use gas phase. And what type of gas phase do you want? You want to use what we call a supersonic expansion. So basically, you have a high pressure gas and you expand it in vacuum, and by doing so, you cool down everything, you freeze the energy, and you reach temperature that are less than 100 K. So that's exactly the kind of environment you do. So here it's represented by you are interested by being in this zone, which is called the MAC disk, and you want to probe material that is here. In other regions, you can have higher velocity of higher energy, but you are in the MAC disk. So we, thanks to the SBIR program, we were able to work with people in Mountain View and to use a long slit source that had been developed in Berkeley by Richard Sekali. We adapted it by adding electrodes to do a discharge, and that's how it looks in the lab. So I'm talking about this fraction of the setup here. So this is a long slit, and you expand through this. Those are electrodes where you can apply a few hundred volts. And the fact is you create a discharge. So you expand gas, and when it's going out, it's going through a discharge. So that's how you provide the energy. And out of this, you have a planar expansion. So you have a region where you've come as close as you can of a free-flying molecules or ion cold being in space. It's surrounded, there is a carrier gas, which is argon, which surrounds your molecule. So this is a simulation chamber. So why it's being used? Basically, you have, you create a high difference between the potential being applied to your electrode and the grounded body, and you create a plasma. So you have electron, you know, plasma is a state by itself of matter in a sense, and you create electron that will be used to ionize your gas when it comes out. So this is a visualization of the planar expansion when it comes out, which is like a cloud of gas basically expanding on your chamber. Remember, of course, the pressure in the chamber, the density is much higher than would be in the diffuse ISM, but that's not the case. What you have seeded in your expansion is in condition as close as it can be to those conditions. So we have a plasma inside with a few microsecond interaction, and we know that some chemistry will be taking place inside, and I will come to this because that's add another dimension to the problem. So we try to understand a little bit, because we're talking about lab simulation again, so you try to fit. So what is the temperature representation? So that's a supersonic flow before any discharge. So you can see that as soon as you exit your slit, where we probe the molecule, which is about here, you are around 40-50 K, which is a perfect domain of temperature. And that's the same representation along the cross-section from room temperatures or higher, because I should mention that the pH are solids, very refractory, so you need to heat them up to increase the vapor pressure. So you have this extra challenge of beginning at hot temperature. You can be at something at high, at 400 Celsius, and you want to bring things down to less than 100 K. And that's how you do it, by the supersonic expansion. And now when you apply the discharge, that's again a cross-section, your gas goes through, here is the discharge, and this shows the electron density. So you create relatively high electron density in your gas, and that's important for the physical property of your sample. And when you map these things, remember you have argon gas seeded with pH, you create this discharge. So one of the questions, and you want to claim at the end of the day that you're going to measure the property of a free-flying molecular ion. So one of the questions that came, are you sure that your molecular ion will be cold enough? The answer is yes, as we've seen from the supersonic flow expansion. And on the other side is you're going to get a lot of things, of course, because you're applying this high voltage. So we're going to form argon plus, going to form metastable argon, or we're going to form electron. And what happened exactly? We were very fortunate to collaborate with a group in the Netherlands who are expert in writing models for plasmas, and they use a code called Plasimo, where they can simulate plasma. And the simulation shows here, for example, the electron density. You can see how it varies when you exit from your source, and the type of density, and argon plus and argon metastable. And the message was that the highest density was argon metastable, and that's very important because the way now you form your Pa ion is by interaction with those metastable atoms. It's called the pinning ionization. It's even a soft pinning ionization. So you've created what you were trying to do, which is end up with a molecular ion that's been softly created, I mean it's in the state you would expect from what you know from the diffuse ISM to find it, and it's cold, and you can probe its property. So now the detection, so you put your sample, you brought your solid, the gas phase, it was warm, it's cooled down, now it's a free jet, and you want to detect it, and that's where the cavity ring down comes into action. And this shows one of the arm of the cavity ring down in the same chamber we're looking at now. So the laser, you inject the laser light through here, and you probe the gas at the exit of your PDN, and you measure absorption. And that's what cavity ring down, that cartoon shows. It's basically, you inject just one pulse by pulse of 1 lambda of laser monochromatic light between two mirrors that's coated with a special coating, very high reflectivity, like 99.999%. And then you measure what leaks out, which is a slow leaking. So if you have an empty cavity, you tend to have this slope. If you put some gas in it, the slope change. And by measuring the variation of the slope, you get a direct measurement of the absorption, and a very sensitive one, and you gain like 10 to the third to 10 to the sixth. In fact, that's open suddenly the window to measure, again, I insist, to measuring gas phase for this large carbon molecule, which is a big challenge. So putting all of this together, we're able to measure for the first time the spectra of some pH like naphthalene, acinaphthene, and others in the gas phase. So now these are the spectra. What you see, this is the bands within one electronic transition, and that's the transition between the vibrational level in one of the electronic states. They are called vibronic bands, and those are intrinsic profile. On the side, you have van der Waals clusters that have been formed because you are in a supersonic jet, so you get some of this, but they are easily deconvolved from the spectra. And out of this, you can now measure frequency and band profile, which we claimed and showed are intrinsic profile. And why is this an intrinsic profile? Again, because your molecule it's cold, it's isolated from interaction, and also in this specific case, we were fortunate to be able to measure to a totally independent technique that's been measured in Orsay in France by using a laser kind of desorption technique with van der Waals cluster and confirm the profile of the band. So we have at least two independent ways to show the profile of the band. So, and this is for acinaphthene. So those features are the one we will need later on, as you will see, to go back and check against astronomical feature. Yes, Stephen.
So the width there is pretty narrow. So you're expecting an electronic transition, which is very vertical, so that what you see, the broadness of this is a vibrational rotational manifold under this electronic transition?
No, what we believe, that's a very good question. Actually, what I'm going to show you, that the thing we learned from that is that the excited state on those Pa ion who are doublet are very short lifetimes. So this is a lifetime broadening. So you're talking about a few tens of femtosecond state. It's an excellent question I'm going to show you. And that's what we learned from that. In a sense, we expected narrower band. So the lesson we get, like naphthalene, you had an average of 25 inverse centimeter bandwidth. So I like to show this because it kind of illustrates what I was saying before. The black curve are the matrix data. The blue curve are the gas phase data. And just by looking at this, forgetting which technique is used, it just makes the point why you needed to do it in the gas phase if you want to go and compare to the astronomical spectra, because you can see the shift of the band and you can see the broadening also. And here the bandwidths, you can see there's a factor of 4 to 5 between bandwidths. So now you can compare band profile and now look for specific because it's very important to be able at some point to detect a specific organic in space. So we did some other measurements going higher in size. It's more challenging because you need higher temperature regime to bring them to gas phase. So those are some cases of pyrene, and you can see how for example, this band is broader even than the naphthalene, and the reason is in the case of this band, if you remember the curve I had before for the compact pH, you probe high energy side. The strongest feature tend to be on the high energy side. So you higher in energy, so you get more interaction between electronic states, so you get a broadening of the band. In the case of the linear one, like naphthalene, you're in the lower energy side, so they're slightly narrower. So the big lesson we get is that the vibranic bands of Pa ions are broad, much broader than many or most of the narrow DIBs. So let us with a comparison with one class of diffuse interstellar bands, a broad one. If you remember, there were bands, a few DIBs of the order of 20, 30 angstrom bandwidths, like the 4429 DIB, which is very famous. So we tried now like to compare data from the naphthalene plus or the pyrene plus to band like this. And we used, in the same time, a group in Boulder, Colorado, Ted Snow and colleagues had done a very thorough study of this diffuse interstellar band at 4429 by taking large number of stars. OB stars are usually your typical DIB stars, and looking to at high spectral resolving power, looking to the profile of the band and really trying to get a sense of what's the best fit. For example, an interesting thing is you noticed the Lorentzian fit works better than the Gaussian fits, and Lorentzian fit is often used for molecular shape structure. And the important information also is that the intrinsic bandwidths tend to show a lifetime of the order of a few tenths of femtosecond. And high resolution show that there is no substructure. So it's really the intrinsic profile of the band. So that's important because it goes along with a polyatomic system having a lot of non-radiative interaction in the higher level in the electronic states and the energy transfer. So that's one other lesson. You have the broad DIBs have a lifetime broadening. So now if we compare to recently, I tried and went through all that's been measured today, not just by us, but the few other labs that do this kind of job. And I think just looking to this list, it shows that each measurement takes time and it's not an easy task. That's a challenge of working with those complex systems. But basically, this is the kind of systems been measured so far from 10 carbon atom all the way to 17 carbon atom. And that's the measurements of the bandwidth of the feature. And here is a 4428 DIB, which we've just seen since it's been well measured. And the point made here, the first conclusion was if you talk about Pa ions for the DIB, you are not going to explain the narrow DIBs with Pa ion, but you may explain the broad one in terms of, roughly speaking, same order of profile. So that's the conclusion number one. Of course, it makes the problem more difficult because looking for a broad feature in astronomical spectra is much more difficult. So lately, very lately, there have been some search for that, and there have been some claim. I add interrogation mark because it's a very difficult case. I'm not sure, but people have been looking for the naphthalene. Here's the spectrum, looking for the strongest band. Of course, if you go and look in astronomical data, you will first try to look for the strongest band. Otherwise, there is no point of looking for the other one if you can't find the reasonable reason for not seeing the strongest one. So this is a 6707, and they found an object in a kind of Cernis 52, which is in some sort of not your average DIB object, but why not? Because again, you can, mechanism of formation will be different. And they found what they claim is this broad feature, not the narrow one, which is due to lithium one, not the broad feature underneath. And they looked at that, they did very nice stellar modeling, and they looked at the band, and they also looked to the other band, the following one in strength, the 64-18-8, and they claim that on the edge of this feature they see something. So it shows you what kind, the challenge of this kind of comparison now when looking for broad feature. But anyway, they've seen that for naphthalene, and there is a mention also of anthracene. So it's a maybe. That's a brand new observations. Another observation on the context of the DIBS is not for pH, but for a carbon chain. But it's related to that, because that things are related to things being formed on combustion or in a discharge. And lately, there's been a discussion about the diacetylene cation. This is the cavity ring down spectroscopy of one band shows, because it's cold, you can deconvolve the raw vibronic bands in this case, and compared to a new diffuse band that the envelope kind of fit with this. But I think, to me, it's still not a case. You need to confirm that to see another band. Yeah?
We know that the near-infrared bands are dominated by the ions, right? Because
For those chains.
Near-infrared bands, right?
Yes.
And that's because the dipole moments, oscillator strengths are dramatically increased when you ionize.
Yes.
Right. So that even though it may not be highly ionized, the ions dominate the spectra we've seen. But in the DIBS, which is the electronic transitions that you're looking at, there wouldn't be any particular reason to think the electronic transitions would be any stronger in the ions than they would be the neutrals. So what about electronic transitions in the neutral pods explain the narrow band?
It's a very good question. Actually, I'm coming to this. So you, yeah. I mean, remember, there is no reason to exclude one versus the other. The reason, the historical reason for talking of ions for pH, you have to go back to the mid-80s when this was put down. The knowledge at the time was mostly limited to the smaller size PA. And I've shown the small PA are not expected to contribute in the optical. But once ionized, they would. So it was kind of a way, the way I see it at least, I'm not saying of proposing that. And somehow there have been so much effort put, including by people like me, on the ion that slowly the focus has shifted on thinking about ions, but we've always kept in mind the neutral one, and I'm going to show you a comparison with the neutral. I totally agree with you. If you have some sort of a population, there is no reason to expect that you won't have neutral. But I should mention that in the mid-90s, when we did this work with Emma Bakes and Alexander Thielens about mapping the charge, the potential charge of those species in different environments, the diffuse ISM, depending on the shape and the structure, there was a strong inclination for some dominance from ionized species in the diffuse ISM. So that was, but again, it was a model, so you have to I mean, it doesn't exclude the neutron, but you're right, there is no reason of excluding. This is, I would say, is more an observation. I'm just trying to give you a feeling. The field of the DIB has always been through funny phases. High excitement like we had, I didn't show it here, in the early 90s, using the matrix data, we had a very close fit with one of the strongest dips at the time. But then things come down, and people put on the table proposal, like this latest one from Harold Lennartz from Leiden. It's related. They looked to product, they had acetylene in a plasma, so again, it's an expansion, a little bit what I showed you, and the discharge, and they had something, they don't know exactly what it is, that happened to which is this bottom spectrum, to absorb exactly where there is a DIB, a weak broad DIB. So it's interesting again. And again, we remember about the component, we're talking about carbon, hydrogen, some sort of mixture of compact, aromatic, non-aromatic. The story, well, I'm trying to put a positive note on this, that the story is slowly kind of taking shape. You have a very complex issue which is probably analogous to a combustion process, which we don't even understand on Earth. Here we're talking about space, and that's eject a lot of a soup of material. And then to prove or disprove something, you have to go to the totally other extreme and do basic lab research on one single element and put all the effort I've been showing to measure one data point. So it's this discrepancy between the astronomical scale and the lab scale that is both difficult and challenging, but also very good for science, I would say, because it's by asking this question that you get with new result. I would remind you, probably you all know that C60 was discovered exactly in cases like that, people working on the DIBs, trying to find something. So just to briefly summarize the ion before going to neutral, we've seen this list. So I was going back to say, okay, here's what we got now, tentative detection of C10H8+, a claim for anthracene, and we've learned from the lab, from the gas phase data, we measured that the bandwidth of the ion, even if you take the smaller one, you will have to address only the broad DIBs, not the narrow one. So somehow we've constrained the problem. And from this type of comparison, you got colon densities of the order of 10 to the 13th. And hydrocarbons, there are this nice suggestion about diacetylene of some product from plasma in acetylene. So again, it's pushing us toward carbon. So that's, I would say, the status of the Pa-ion hydrocarbon versus the DIBs today. But of course, they are neutral, as you mentioned. Measuring neutral is a totally different game. It's simpler because neutral molecule much easier to deal with than ions in the lab. Ions are really tricky business. So here, basically what we've done, we use the same planar expansion. We do a discharge, we warm up the Pa, a discharge, but an expansion, no discharge. So you have a neutral. And because it's cold now, you're able to deconvolve somehow your spectrum. And these are relatively large molecule like perilene, benzoylperilene, you're talking about 22 carbon atoms. Keep that in mind. And that I like to show because one of the criticisms to the Pa model in general, especially people working in radio astronomy, was that the fact that because they're big system, you always have broad features, you can deconvolve them, so you have no way really to pin them down. But now by using things like supersonic expansion and free jets, you are able to cool down things sufficiently to deconvolve them, and you can have spectra where you can go and compare to astronomical spectra. So here, because of the criteria, we can double check the temperature from molecular point of view, looking to the envelope of the band, we get 50 K. And also what we learned from here is that the bands are really now for neutral pH, the bands are very narrow. That's what we need to remember as opposed to the ion. And those bands, now you can turn back to the family of narrow DIBs, which are very numerous. So again, this is exactly making the point you were asking. So we had some of them measured here on the formula, and this is where we had transition. So you take these things, turn back, and go to the astronomical observation and try to see if you can, now that people can do really high quality astronomical observations, so been collaborating with many teams, including people working at the VLT and stuff, and try to see can we get signature. So lately I had this ambition trying to finish, it's to update the survey of the 90s I showed to you where we compared the matrix data to the DIB. Now we claim, at least I claim, that we have gas phase data, so it's yes or no, because that's what really we want. So by collaborating with my colleagues in Poland, Jacek Kralowski, who is a DIB expert, and Gazinur from Russia, we've been doing this kind of survey. So basically it's a case by case. You take your molecule, go check for transition, do high quality astronomical data, very low noise, and try to put an upper limit, just for the sake of it. In a specific line of sight, for the specific Pa, your upper limit, either you see it, great, we jump to the sky. If we don't see it, here is the upper limit. But try to put some uncertainty. So we've been going, you can see the kind of limit that's on this spectra. So again, you look for the strongest feature. No, you don't see it. We looked for phenanthrene, again here, the spectrum, pyrene, which is at shorter wavelengths. As you know, it's more tricky to get better data when you push to the, here you're pushing to the limit, the cutoff because of ozone perturbation. And all these things come from, again, a relatively good database of stars with all having just one cloud in the way. So those are line of sight with single cloud to avoid the issue about the effect if you have more than one cloud, which you sometimes do in some of this line of sight, going up to benzo JSI and so forth. So basically, this is what we are up to now. This is just work being in preparation, so we are still working on this, but I wanted to show you the latest and where the lab took us now in terms of comparison, so we can really work. Of course, you can't measure all molecules and you can't go and check all molecules, but you can get some feelings by doing this type of comparison. So basically by going back to the system and in each case, we can only put an upper limit since we don't see the strongest band. You can derive colon density, upper limit to colon density, if there, which are range from about 10 to the 10s to 10 to the 13s, and how much, of course, abundance, relative abundance, this would be. So this is where we are with the neutron. But there is a very important, another issue, which I thought was interesting with the neutral pH. Here we've been looking for bands. So number one, for position, for stronger band. But in one case, here, again, it's the same kind of things. You have many DIB objects, and the average of all those objects to improve the signal to noise. And that's compared to pentacene, which is a linear molecule, a nice gas phase, free jet, cold, everything. And now, of course, when you look to that spectroscopy, that is not in the spectrum, because if this band is so close, where is this one? There are no stellar features, there is no reason we can see to exclude this band, so it cannot be this one. But if you push a little bit and compare the profile of the band, those are narrow features. Now I've shifted this by about 2 angstrom, which is a shift between the two bands. So we're not talking about a fit in position. If you look to the profile, you can see exactly your question, Stéphane, that the neutral band profile are really shape-wise fit the narrow DIBs. So that's the other lesson we learned. So this is what we got in terms of comparison of profile. So just to summarize, let's say what we got is really we learned ion versus broad Debs, neutral versus narrow Debs. We didn't get a fit of 1-to-1, but in a sense we're in a more firm ground now that you know that the things are slowly coming together. And I would like to say also a few words, without extending too much, about another project we're doing with the system, which happens to be related to the DIBs. The idea was, because we had this planar expansion, because we have discharge, we noticed we have a plasma. Having a plasma means that you can form a lot of stuff. So we decided to see if we could have some contribution to the understanding of how larger species of carbon grain can be formed from pH precursors. Since if we assume we have pH, so in the outflow of carbon star, that the current model in the community, so you go from smaller carbon feature to bigger, and that's how you explain carbon formation. And why did we think, did we got about that? It's because while doing the experiments, for example, for ion like pyrene, that's a typical voltage we use to form softly the ion, 500 volt. And when we look to the effect of increasing the voltage, we happen by sheer luck to see a band associated with the fragment CH. Why tear-like? Because when you do cavity ring down, you're limited by the wavelength response of your two mirror, which is usually the lambda peak plus or minus 12%, and by the wavelengths of the laser. So in this case, the transition was close enough. And what that shows you is that if you can break them in the discharge, you can have all sorts of chemistry and building up. And of course, we noticed that when we increase the energy of the plasma, we observed some soot-like deposit on the electrode. And when we gave this sample to, we have the chance to collaborate with Dick Zer's lab in Stanford, where they have a very sensitive laser desorption mass spectroscopy technique. We could see spectra like that. That's if what you put in, for example, in this case, it's anthracene, 150 about mass unit. This is what you measure in your soot. You see larger products. So there is evidence of stuff growing. So, wow, that's interesting because, again, remember, we are simulating as close as we can some interstellar environment, so you can try to look to stuff like that. But beside this, what this is also important for is that in your discharge, you are going to create more exotic species that you cannot intentionally put in your system, but that may also be related to the DIBs, because there is no reason that the DIBs or the infrared bands be explained by just the regular compound as you have it on Earth. So that's led to the last part we added to the system, which is basically with spectroscopy alone, as I explained, to do cavity ring down spectroscopy, you need some pre-knowledge. You need to know where the species are going to absorb, and we had that with the matrix. But now when you go in the unknown plasma product, you can't look with it with cavity ring down. So you need another analytical tool, which is here mass spectrometry. So we recently mounted the reflection time of flight mass spectrometer. The idea being you get your expansion, your discharge, you create stuff in it, you detect it with the mass spectrometry, by definition much more sensitive than photonic spectroscopy. Then you try to make out what are those things, at least roughly, and then turn back and try to measure the spectrum. So that's where, and that shows a new addition to the system. So that's basically the tube of the time of flight. So that's heavy hardware to measure molecular things, and this is the source I was showing to you. So basically you close this and your beams come through, a pulse force it to turn 90 degrees where there is a reflection and a multi-channel plate. And that's one of the first spectra we've been measuring, beginning with, in this case it's methane, because just picked a spectrum. That's the Titan studies where we look to fragment. It shows all the field you open also this way. So the hope is to form a species we can measure. So I would like in conclusion to get back. I think I said already most of this, but the question was what we do is low temperature spectroscopy. So that's in the case of this species, this is what we've been doing. And what we learned, we learned a lot about the spectral characteristic of this molecule. I should mention also that makes Ames and a very few labs were the expert in this domain. Why? Because polycyclic aromatic hydrocarbon, being very refractory, very heavy system, difficult to bring to gas phase, tend to contaminate systems. So many basic research lab will be reluctant to study system like that. So you really need to dedicate the thing to a given project. And from the PA, of course, that's opened up to carbon in general. We're not limited to pH. We're looking to any species that address the issue. The focus in near UV to infrared range. So now we have intrinsic band position and band profile. And that's, for this scale of molecule, is, I think, the achievement we've all managed to do over the years. It brings this field to the level where you can really take one given spectrum and compare it. And now we are actively involved in observation with many groups, and including VLT consortium. And also with, as you know, the cosmic origin spectrograph is now running on the Hubble Space Telescope, been delayed for years. And the kind of data we have are really important to one of the science priority of COS, which is basically looking for the signature of organics on the extinction curve. So to do this, again, you need some specific transition measured in the proper condition and go and measure. So now where we're going with all of this is, again, trying to find, as I said, would be really important to be able to find the signature of a specific PA. It may not be possible, not just because the lab is limited, because again, I hope I convince you how complex are these issues. So if you have a distribution of many carbon species, it may be because you can't, even observationally, I mean, you may have just a broad feature that convolved on the feature, but we still need to try to look in the UV and in the far infrared with Herschel on the other hand to try to pin down specific molecule. And again, searching an extinction curve, and also we're working on carbon grain formation. So I guess that's it. I want, of course, all things like that are done by a lot of people, and I want to acknowledge current fellows who work on this, and all the people who've been working on this over the years, so, and all the collaborators who have made this possible. And thanks for your attention.
Fareed, I was wondering if you could say a few words about the PAR database that is coming up online.
The infrared database.
Yes.
Yeah, there is a. It's almost ready to go online. That's about the infrared database has two components: laboratory measurements of infrared transition, infrared absorption, so the vibration of pH in the ground state. So that's a very valuable tool for infrared astronomy, and also all the calculated, the theoretical work. There have been a lot of work done over the year between Stephanie here and Charlie Bauschleicher and many others, and the modelization done by Jan Kami. And I think there is even an address. I wanted to bring, there is even a poster for the database, which we had, I think was released at the SCS last month. So the database is coming online, yes. I don't have the exact address, but I can send you to you. And from the UV viz, there is also a database, but it's not yet on the same. But I should again. I hope also the difference I wanted to make for the infrared. You need to take many spectra and convolve them because you have a distribution of pH. You're not going to feed the infrared emission band with one pH. In the UV viz, you're looking for a signature of a specific one, so you need single individual spectra.
So I know that as these get larger, they get refractory and they're hard to get into the gas phase. But there's some evidence that highly symmetrically, very larger ones like coronine or circumcoronine may be part of the picture, at least in the near-infrared bands and potentially in the DIBs. Can you get coronine, a spectrum of the neutral coronine?
For now, benzo GHI coronine, which is coronine -1 ring, is the highest we could get. And the reason is simply that you need to find the ways the free jet expansion, the PDN works. You have this rubber kind of shaft that goes and seals the opening, and it's pulsed. And it's, we've been able to find material that goes up to about 350 C. And it's, the challenge is at this point, the whole block has to be brought to this temperature. So I think for the larger PA, the future is more in laser desorption, that you shoot with the laser. But it has its own problems too, because when you begin to form a plume, you get all these things. So we were wondering about that. That's what I'm trying. This is a typical problem where you have to go in the direction of what astrophysics tells you. You want to go larger complexity, higher system. And it seemed that at some point we may meet kind of a physical limit of, it gets really complicated. And I should mention also something, there is a cost issue. When you want to get the higher one, the price just is prohibitive. So there is no way because the higher they get, the more isomers they can get. So apparently to make them, synthesize them, is very expensive. So in some sample, if you ask, you can only access like a few milligram, a few micrograms. So for now.
Thanks for this wonderful talk. And I was wondering, there's more than one way to produce ions. In these cases, you could also remove a proton, a hydrogen plus minus an electron. Would that be another way of producing ions that have distinctly different, of course, they will have distinctly different optical properties?
And I would say at this stage we don't know, even when playing with the condition of the plasma, what you form. You form all sorts of stuff. That's why this is a very rich field. But again, I'm trying to say the way the process been thought of, you begin with an issue which is take a pH, ionize it, hopefully one photon process, because again, we're talking about simulating, and give me the spectral signature. So the whole thought was oriented this way. So that's why, for example, using a discharge was just a way of forming ion in a soft way, and the whole source being optimized to do soft spinning ionization. And now, for example, to study grain formation, you may not want your pinning ionization to be that soft, exactly because you want to form, and I hope that with the mass spec we can begin to see this kind of species. Now the challenge would be to go back and figure out where would they absorb and how would you measure the spectrum, but it opens at least, again, we can't, no one in the lab is going to probe everything, but we need to get the signature of prototype of different classes, and that's what this is about. What I should mention, because I do this often about pleading for laboratory astrophysics, and when that's another illustration. For example, doing this PDN, we had a plasma. I'm not a plasma physicist, so we thought, okay, we have a plasma, it must be an average. And when we worked on it, we found out that it's an unusual sort of plasma. It's an afterglow because it's been done in condition, lower pressure, and so forth. And suddenly there was a lot of interest by people, like people doing the placebo and stuff. So even for basic plasma science, there was interest. So that's why it's so important to do. Yeah.
Farid, as a memento of your talk, we'd like to give you a SETI pin.
Thank you.
That hopefully will bring you luck in finding the right bands for the DIB.
Thank you.
If you'll join me in thanking Farid.
Thank you.